Hey guys, welcome to part 2 of chapter 15 for Chem 112. Now, when you left off, we had this equation. I'm trying to solve the numeric value for K, and I started filling out this chart. And in the problem, it said that the initial concentration of CO was this, the initial concentration of hydrogen was that. Now, there's a little something at the end of that question that tells you the equilibrium concentration of CO is 0.15. And I can't remember if I said this in the last video or not, but here's what this table means. It has all of my reactants and products. These are the initial concentrations. This is going to be the change, and this is going to be the new concentration at equilibrium, ice. So if these are the two concentrations of the reactants when you start, you don't have any products. You haven't made any yet. It's the initial, okay? Now, this is the initial, and this is where you're going to end up at equilibrium. So what's the difference between these two? Well, you lost 0.35, okay? And here's the dealy poo-poo. I love math. I love proportionality. If this loses 0.35, this has to gain it. Why? Because this has a 1 in front of it in the balanced equation, and that has a 1 in front of it in the balanced equation. Well, if you look here, this has a 2. So this is on the reactant side. It's going to lose 2 times as much of that. Okay? So 1 minus all that means my equilibrium concentration is going to be that. 0 plus that means my equilibrium concentration is going to be all that. Why is that important? Because those are the numbers you have to use right here. So K equals the equilibrium concentration of this. That's 0.35. Over that, that's 0.15. And that, which is the H value, but that's going to have to be squared. Okay, put all of that in my calculator. I'm at 26. I'm done. The key to all happiness with these types of problems is using this chart. Is it laborious, tedious? Perhaps, but you'll never get one wrong if you use it. Okay, now I'm going to flash up the next example, which is like the one we just did, for you to view at home on your own. See, and you can hit pause to see all of my work if you need to. And I'm going to move on to the slide that says reaction quotient. So these K values are numeric values at equilibrium. What if I want to know the value at any point during that reaction besides equilibrium? Well, you set it up exactly the same way, but you give it a different letter. And that different letter is Q, reaction quotient. So it's still going to be products over reactants. It's still going to be the same setup. But instead of saying K equals, we're going to say Q equals. It's the reactant quotient. Well, here's the dealy poo-poo. If Q is less than K, if I tell you to solve for Q at this point and solve for K, and Q is less than K, the reaction is going to head to the right. If it's greater than K, it's going to go to the left. And if it's equal to K, it's going to be at equilibrium. Okay? Now, I want to do a few more examples with you. So I'm moving on. Let's go ahead and do this pressure, this KP example from your notes. Okay? So, from your notes, I gave you this equation. And all of these are gases, so I'm not going to put the G there. But I told you that KP is 81.9. And I gave you some pressure values for all of these gases. And I said, is it at equilibrium? Well, I don't know. If KP is equal to K, then we'll see. We'll see what the KP value is. So KP is going to be the pressure of this squared, because there's a 2 there, over the pressure of this times the pressure of that, okay? So I'm setting it up the same way, products over reactants. Instead of doing the brackets, I put P for pressure. That just kind of keeps me straight. And I use the numbers in the problem. In the problem, it says this pressure is this. And so I'm just plugging in numbers, which is really easy for you guys because you're really smart. And then I end up with 10.8. So what does that tell me? Well, that tells me that Q is less than Kp. Because here's Kp at equilibrium. Here's Kp just during the reaction. This is less. Q is less. So if Q is less, the reaction proceeds to the right. Okay? Easy peasy lemon squeezy. Let's do a few more examples. Okay, let's see. I want to do another example where I use the ice strategy, but I want to do one where we have to use the quadratic formula. So I'm going to show you this example from your notes. I want you to pause on it so you can see my work, okay? But know that I'm going to this example. Why am I bumping to this? Because I am worried that even though you guys are superstar math students, you may have forgotten some of those things in middle school, like the quadratic equation, all right? So I'm looking at the example in your notes that is N2O4. And these are both gases, so I'm not going to write gas. And I tell you that Kc is 0.36, okay? And so that's the information that's given. And the first thing you're going to want to do is you're going to want to go ahead and write the equilibrium constant for this, okay? And so I know that equilibrium constant is products over reactants. So these are my products over my reactants, okay? Easy peasy, we've been doing that for a while. And oopsie daisy, that did not go the way I expected. And then, because I know that I'm kind of given all these and I'm looking for change, I'm going to make my ice table, okay? ICE. And so I'm going to have N2O4 there. And I'm going to put this 2 here to remind me that that's going to look like that. Now, in these problems, they're going to give you initial or equilibrium concentrations, and you're going to be finding one or the other. So in this problem, it says that a reaction mixture initially starts with 0.1 molar of that. If that's what you start with, this other box has to be 0. That means I don't have any of it. All right, that means that the change, I'm going to gain some there. I'm going to lose some there. Why? Because I don't have any here. To get to equilibrium, I got to have a little something. And y plus x, I don't know how much I'm going to gain. But whatever I gain here, I'm going to lose there. So I'm going to gain it here plus x, lose it there. And so the equilibrium concentration 0 plus x is that. And then, oh, excuse me. Oopsie daisy, I forgot to put my 2 there. And here I told you to make sure if there's a 2 here, there's going to be a 2 there. If there had been a 3 there, there would be a 3 there. I got so excited, I was just running on through. So when I look at this, I have 0.1 minus 2x. Again, why the 2x? Because 2 is in front of it in that balanced equation. So now, I'm going to start filling in this and see what this starts looking like. And it is going to be a little crazy too. So K is for equilibrium. At equilibrium, this is the equilibrium concentration. And at equilibrium, that's the concentration of that. Okay? Now, here's what I did. The first, oh, and then I know K, whoopsie daisy, is 0.36. The first thing I did was get rid of this x, and I moved it over here. So I ended up with 0.36x. And then taking it back to Algebra 1, I'm going to do some FOIL. First, outer, inner, last. Okay? And when I did that and I summarized it, I got that. Now, why did I rewrite it so x squared, x, and then the number are there? Because when you have x squared and x, you have to use the quadratic formula. And to use the quadratic formula, that's the way it has to be done. So you should remember from algebra when you're solving for this, that's what you have to use. And what that means is this is the number for A, this is the number for B, that is the number for C. So I'm just going to put my numbers in. Okay. Now, when I solved that both times, once for adding, once for subtracting, I got x equals that, or x equals that. All right? Because we are super math students and super scientists, if you start with 0.1, you can't react more than that. This is more than 0.1. So that can't be the right one. So that has to be the value for x. Are you done? No way. I asked you what the equilibrium concentrations were. So at N2O4, the equilibrium concentration is x. Can we see all? Yes, we're still on the screen. Okay. And then for NO2, the equilibrium concentration is 0.1 minus 2x. So when I put all of that in, I find out that that is 0.072. So those are my answers. The one thing I am super concerned with, and I know I kind of went on and on about it, was the quadratic formula. Yes, you have to know it. Yes, you have to remember it. I will not give it to you. Okay, but I know it's been a while. All right. The last thing your textbook talks about is Le Chatelier's principle. Le Chatelier just said if a system's at equilibrium, if the rates are the same forward and backwards, and I do something to adjust that, okay? If I do something to change it, what's the system going to do? Well, the system's going to react so that it's going to react so that it goes back to equilibrium. Sorry, I stumbled there a little bit. So I want to go through, all of these are gases, okay? If in a system that was at equilibrium, I remove some of this. That means this side's getting smaller. I want to make some more of it to make it equal again. So the equilibrium would shift left. If I added something to that side, that would mean this side's getting bigger. I would shift and make more of this. So I would shift right and make more of that so it would become equal again. Think of it as being on a seesaw and Biggie gets on and you're trying to level the seesaw back out. Okay? Temperature. If this is endothermic and heat's over there and I heat it up, that means this side's getting big. So it would shift to the other side. Now, the last thing that I want you to remember with Le Chatelier deals with pressure. I can change pressure because when I change pressure, it affects volume. And if you increase pressure, it's going to shift to the side with the fewest gas molecules. So this would be the side with the fewest gas molecules because there's a 2. 1 plus 3 is 4. Okay? This concludes all of your Chapter 15 notes. I can't wait to see you in class. Toodles poodles.